Okay, so when having such kind of an equation, the first thing that should come into your mind is to try and sketch the real thing happening here. So we're having this is it 0.3? Yes, 0.3 kg back here, and then we are having one which is coming. They're saying it is initially moving along the x-axis with a velocity of 9.1. So it's coming, let's say, from this direction with a velocity of 9.1. So let's take the v to be 9.1. Okay, and then this is having the mass, let's call it ma, of 0.2. okay, so this particular pack, it hits this and then moves in the positive x-axis. Okay, it moves in the positive x-axis at this angle with this particular speed. So after the hitting, it gets deflected, moving along this path, which is 53 degrees, and this final speed is 5.5. okay, so now they want us to find the velocity of the 0.3 kg pack after the collision. So our analysis or strategy is going to be like this. We are going to consider the momentum in the x and also the momentum in the y. So the momentum in the x must be conserved, so is the momentum in the y. And how are we going to go about that? So we're going to say and actually let's call this one as mb, since we've called that one as ma. So we're going to have ma multiplied by v1 plus mb multiplied by v1. Let's call this actually va, and this one vb1, and this is going to be equal to the ma being multiplied by va2 plus mb being multiplied by vb2, and that's our variable of interest, okay, the vb2. So all that we have to do is do replacements, but remember this is in the x. Okay, so all the vectors that we are going to consider are only in the x. So if we start doing the replacements, this is 0.2 times v. We look at the velocity, which was at 9.1, and all of these was in the x, so 9.1. If it was coming at a certain angle, then we could have only gotten the x component of 9.1. But in this case, since all of it was in the x component or in the x direction, we are going to get all of it. Then from there, we're going to add mb, which is 0.3 multiplied by 0, 0.3 multiplied by 0, which is just going to be 0 anyway, is equals to ma, which is 0.2 multiplied by the final velocity of the smaller block or the smaller pack. So this one, we are told that it was rushing at 5.5, but it was at an angle 53 degrees. Therefore, you're just going to get the x component of 5.5, and then here we're going to add plus mb which is 0.3 multiplied by our variable of interest. So let's just find the value of this, take it the other side, and then we do the mathematics here. Okay, so 0.2 multiplied by 9.1 gives us a 1.82 is equals to just a minus 5.5 cos 53 multiplied by 0.2 gives us 0.66. okay, 66 then is equals to 0.3. let's go it VB2. yes, so we do subtraction, minus 1.82, we get a 1.158 is equals to 0.3 VB2, and therefore VB2 is going to be equal to 3.86. okay, 3.86 meters per second. So this is going to be the final velocity of the 0.3 kilos per. Okay, so the value that we found here is in x. okay, so we need also to calculate that of the y. So in calculating that of the y, we're just going to say in the y we're using the same formula. okay, so we're just going to say initially in the y, the mass, which was 0.2, had the velocity of 0 in the y. okay, in the y it wasn't moving. When you look at our diagram, it wasn't moving neither up or down, it was just in the x, so 0, plus of course the momentum of the stationary park was 0, is equal to in the y. okay, in the y we had our small park, the 0.2, moving at the speed of 5.5 sine 53. we are getting just y component of that, plus the 0.3, let's call this one VB2y. okay, so all this will result into a 0, and then this would become 0.2 multiplied by 5.5 sine 53, and that's going to give you 0.87. so VB2y is equals to 0.87 divided by 0.3, and to get a 2.93. okay, so meters per second. Now all we have to do is just to get this one and this one and make a complete vector. So our VB2 is going to be VB2x squared plus VB2y squared. So which just means that 3.86 squared plus 2.93 squared. okay, this is a 3, and minus 3.86 squared, then square root of the answer 4.8. meters per second. Okay, so that's our final answer. Okay, so lastly, we just need to calculate the fraction of the kinetic energy that was lost in the process of collision. So all we just have to do is to calculate the kinetic energy before and the kinetic energy after. Okay, so having the after and the before, we'll be able to compare and see how much was lost. So before the collision, the kinetic energy that we had is half mv squared, which is just half of the 0.2 multiplied by 9.1 squared, and this is going to give us 0.2 divided by 2 multiplied by 9.1 squared. That's 8.281. And then this is going to be half mv squared, which is half of the 0.2. So this is going to be the summation actually. So half of the 0.2 multiplied by the velocity, which is 5.5 squared. We add half times the 0.3 multiplied by 4.85 squared. Okay, 5.5 squared. This gives us 3.025 plus, we're going to get 0.3 divided by 2 and then multiply it by 4.85 squared. That's a 3.353. 3.53. So if we add the two, we're getting 6.55. So when you compare these two values, we'll compare them by subtraction, and therefore we're just going to do 8.281 minus 6.55, and we're going to get 1.73. Okay, so the difference is equals to 1.73, and therefore we're just going to say the fraction will be 1.73 out of 8.025. Let me see if I got that correct. 8.281. Okay. So this is the fraction of what was lost. So you can just convert this into a decimal number. giving you 0.21, which is approximately 21%.